Can you imagine? And also, if I swear, someone might like cut me into one of those YouTube songs where I'm like, oh, it's now recording, is it? Okay, no swearing, anybody. Right, so formulae and equations. Okay, we'll look at word and symbol equations, and then we'll look at some formulae that you need to know. Relative atomic mass, relative formula mass, moles, and we'll look at percentage by mass quite quickly. And then I've got another PowerPoint specifically on your moles, and then I've got some stuff on quantitative equations, which brings in empirical formula as well. Now, when I was saying to you guys before, formulae, and then some of you were telling me equations, you're often telling me physics equations, that's what is different in chemistry. In chemistry, formulae is when we're looking at something which tells us about a specific molecule. Equations tell us about a specific chemical reaction. Does that make sense? And the only equations you need to know are word equations and symbol equations, and try and balance them. Alright, let's go. So, a word equation is what we did in the olden days when we were back in year 7 and we started doing chemical reactions. And a word equation just is the word for what's happening. So, sulfur reacts with oxygen to make sulfur dioxide. It's useful because it's easy to do, but it's not useful because you can't tell how many atoms are involved, and you also, you might not know what's going to be made. Does that make sense? Now, the cool thing about symbol equations, by the way, when you react sulfur in oxygen, it makes this lovely blue colour, so that's why they put that there. But when we use symbol equations, we get a lot more information. Anyway, let's have a look at some practice ones. So, magnesium plus oxygen, give me the correct answer, Hunter.
Magnesium oxide.
Magnesium oxide, okay, you've been doing this long enough, so that's nice and simple. Check, you're absolutely right. Copper carbonate makes copper oxide and what, Maylis? Carbon dioxide, yeah, that's a decomposition reaction, so well done. Zinc carbonate reacts to form carbon dioxide, but what would also be there? What do you think, Ishita? Zinc? Zinc oxide? Is that your final answer? No, you were right. I was checking you were confident with it. Sodium hydrogen carbonate, it will decompose carbon dioxide and water, but what will be left behind? What do you think, Tiff? If you had to choose one of those, what do you think the blank is? Hydrogen, you think hydrogen's going to be there? No, the hydrogen has probably gone to the water. Sodium hydroxide? Well, that's not a bad guess. It's not. It has to be sodium oxide. Okay, you're absolutely right. Now, you're thinking, how the hell do I know this? Should I know this? The problem is, the point of doing this is the limitation of a word equation. Unless you're familiar with the reaction, can you fill the blank in? No. And that is why we're doing this. Now I'm going to stop there because we're not going to go through all 6, but that was the point, okay? The point is, don't look so worried, Tiff. The point is that it's not easy. People think word equations are easy. It's not easy. It's only easy if you know what's going to happen. Symbol equations are easier because you know there's a golden rule in science. Golden rule in chemistry. What is that? Atoms can never be gained or lost, destroyed or created. Yes, you basically can't destroy matter. They have to go somewhere. So the cool thing about symbol equation is that this sulfur has to go somewhere and this oxygen has to go somewhere. And that's why symbols are a lot more useful. Even if you didn't know the name of this, which is sulfur dioxide by the way, but even if you didn't know the name of this, you would still be able to get some marks. Okay? We don't, thankfully, have to draw them, but that's basically what this means. The little number here tells us the number of atoms present in that molecule. Okay, the little number tells us the number of atoms present in that molecule. So H2O tells you it's 2 hydrogens and 1 oxygen. Okay? What about big numbers at the front? What do they tell you?
How many of them?
How many of them there are, the multiple of them, yeah, okay? So here we've got some examples of interpreting some symbol, or actually in a sense these are all salts. But basically, remember the little numbers tell you there's 2 atoms of iron and 3 atoms of oxygen. Okay? Are you all happy with the state symbols? Yeah? So we add the state symbols because it gives us a bit more information, gives us more idea about the story. If you see a little brackets with S in, what do you think that's going to be, Tiff? Perfect, yeah. Liquid is L, G is gas, and the only other one you'll come across is AQ, which actually stands for aqueous.
Is that when H2O is in the equation?
It's when, not when H2O is an equation, it means it's used as a solvent. It's when that thing is dissolved in water. So you often see it with acids. So hydrochloric acid is HCl, AQ.
So is this relevant to the aqueous solution?
It is an aqueous solution.
Oh.
I'm not sure what your relevant to it is, but this is what it is. So if you see AQ, it means it's dissolved in water. Okay? Right. We have to balance equations because we know the golden rule is that atoms can never be created or destroyed. And the only way we can balance equations is by putting big numbers at the front. Big numbers mean 2 times or 3 times. If there's no number at the front, how many of them are there? 1, yes. But do we put a 1 in?
No.
No, in fact, Maylise feels hard done by because in her mock, I really tried to take away a mark from her when she actually put the 1 in there. Yeah, but I can't guarantee the examiner will be as nice as Mr. Tetley. So, you must remember that. The big number at the front means that there's 2 times magnesium. And then when we add these up, everything should equal the same. Okay? So we've got 2 magnesium atoms here. We've got 2 magnesium atoms here. How many oxygen atoms have we got here? 2. How many oxygen atoms have we got here? 2. We have got 2 because it's 2 times MgO. There's no 2 in the front here, but that's because the magnesium and oxygen have joined together. And what have they formed? A whole new substance, yeah. Okay? Right, let's have a little look at these equations and you can tell me if you think they're balanced or not. Marvel,
yes.
What about this one here? Do you think it's balanced or not?
Yes.
You think it's balanced, okay.
Yeah.
What about this one here? Tommy, at the back, what do you think? Balanced or not?
No.
Okay, not balanced, okay, we'll copy that. Jordan, balanced or not? Nancy, balanced or not? Balanced. Balanced or not? Hunter,
No.
balanced or not? Adrian, that's a big one, but take your time.
Yes.
Is that balanced, Adrian?
Yes.
It is balanced. So which one of these over here is not balanced?
Bottom.
It's the K one because it's K and then it's 2K on this side. Okay? Can you see how you instantly you just need to check that the atoms on both sides match up? Now, how do you do it quickly? Well, there's no quick way really. You just have to go through them. Here we can see there's 3 oxygens there.
1 there.
1 there, that's 4, but only 2 on this side. The aluminium's balanced, that's okay. Carbon's balanced, but the oxygens don't. Not balanced. Here, we can see that iron's balanced, that's fine. The chlorine, there's 2 there, but there's 4 there, not balanced. Here, we can see there's a K, and then there's K2 on this side, not balanced. The oxygen is O2 and the O. But the problem is, it looks a little confusing, so make sure you check them. If you want to, draw the atoms underneath, and that'll make more sense to you. Okay? If I was doing that last one, I might even draw my K, I might draw my oxygen, and then I'd draw them on the other side, and I need 2 Ks and 1 oxygen, and I'd notice that they don't match up. Okay? Fine. Now, should we have a go at balancing some together? Yeah? Okay, now this isn't the easiest way to balance because they've chosen some things for us to balance, but we can give it our best shot, okay? So, Nathan, have a look at the top one, see if you can identify the problem first of all, and then maybe we'll be able to balance it.
There's 2 hydrogens on this side.
There's 2 hydrogens on this side, So what can we do to this side? Yeah, keep going, you're doing well. Well, what can I do? If there's 2 on this side and only 1 on this side, what can I do? I can add another one, so I'm going to make that 2. Okay, take over Maylise. Is it balanced now?
No.
That one. Hang on. Yes, it is.
Yeah, Hunter, you said no. Why is it not balanced?
Because.
The C is fine. The CL.
Oh, yeah, sorry, my bad.
two and then the
So what do I have to do here?
Nothing.
Nothing. Check it. Absolutely right. Now, often when you start balancing things, the other elements sort themselves out. Does that make sense?
Yeah.
Okay. Right, let's have a look at this next one here. Sorry. What is the problem, first of all? I need 2 Na. Okay, I'll pop that in. Will that balance it?
No.
No, it doesn't, does it?
Oh, it does.
It does.
There you go, you said it. No! But you did balance it, okay? 2 Na, Cl2 because that's diatomic. There's 2 chlorines there, okay? Right, what about the next one? Ishita, what's the issue?
Can you do any on the left?
Okay, let's do that. So we need 2 there, but we have a problem. That balances that up, but then we have too many oxygens. Okay, so I could halve the oxygen, but it doesn't work very well. So what am I going to do? I need to balance my oxygens up first. Leave the sodium for a second. How do I balance my oxygens up? Add 2 on here, okay? So add 2 there. Now my oxygen's balanced. Now what can I do to my sodium?
4.
Then I do it there, yeah. If it doesn't work out easy, leave that element for a bit, try another one. Well done. Let's have a look at D, getting a bit harder now. Adrian, what's the issue here? So I need 2 of those, yeah, and on 1 of those, yeah. Is he right? He's absolutely right, okay? This next one is very tricky. This is like a higher level one, so let's give it a go. Jordan, do you want to start us off? What's the issue? 2 to the hydrogen, okay, because that balances up the hydrogens over there. What about now with my oxygens? What am I going to do? 2 there, did you say? And what about now? You've balanced your hydrogens, you've balanced your oxygens. So what's that going to do to the nitrogen? It's balanced, isn't it? So what will this be? 0. Oh, 1 actually. Don't say 0, otherwise that deletes it. Can't have no matter. But that's absolutely right. Does that make sense?
Yeah.
As you started to work through it, you solved it. Final one, Hunter.
Wait.
Balance your oxygens first.
Oh, okay, so you need to put 2 on that side.
Cool. Now my oxygens are balanced. If I just put that
0
there.
there, 1 there, and then 2 for the magnesium. Right?
Easy peasy. Okay? Balanced equations are all about problem solving, basically. Choose yourself a suitable element, balance those first. Always try and balance the elements that are within a molecule first. Leave the single elements on their own because they mop up nicely. Does that make sense?
Yeah.
Yeah? Good job. Right, relative atomic mass. Now, the relative atomic mass can be found on your periodic tables, okay? It is a number that tells you how heavy an atom is. Atoms are tiny. We can't weigh them in grams because it would be silly. Can you imagine trying to count out grams of atoms onto a scale? It just wouldn't work. So when we want to weigh single atoms, we use a term called relative atomic mass. And it basically means we took carbon, because carbon is a very useful element. It's a solid at room temperature. It's very easily obtainable. You are mostly made of carbon. The table is mostly made of carbon. The paper you're writing on is made out of carbon. It's a very common element. And carbon weighs 12. We compare all other elements to carbon. So hydrogen, for example, is 1/12 of the weight of carbon. Another way of saying that is it would take 12 hydrogens to be the same weight as carbon, sorry. Does that make sense? There are no units for relative atomic mass other than atomic mass units. You sometimes see AMU, but at GCSE level, you don't need to write them down. So when we say, how heavy is a magnesium atom, you just find the relative atomic mass, and it's 24. Okay, so we would say it's 24 atomic mass units, or just leave it as 24. Does that make sense? Yeah? And a magnesium, yeah, is twice as heavy as carbon, basically. So it's almost like you could see into the future, Hunter, because that's the next one more balanced. We'll stick a magnesium on there, and if we wanted to balance our scales, we'd have to put 2 carbons on. Atoms are arranged from the very smallest to the very largest. Okay? We don't use grams, that's not sensible, so we use relative atomic masses, and they're useful. Okay? So, how do you find the relative atomic mass? Well, it is found on the periodic table. Okay? It is the larger number. It could be at the bottom or it could be at the top. I mean, up there it's at the top as well, and here it's at the top. On your periodic tables, I can't remember off the top of my head. And if I have a little peek at this one here, this periodic table here has it at the top as well. So the relative atomic number is the larger number. Then you've got the symbol, and then you've got the atomic number at the bottom. What does the atomic number tell you?
How many electrons there are?
How many protons there are. But protons should equal the same as the number of electrons in an atom. Do they equal the same in an ion?
No.
No, ions are different. Good. Okay. So, let's quickly go through these really quickly. Heck, number 4. Which element has a relative atomic mass of 4?
Of 4?
Yeah, you might have to have a peek at a periodic table. And while Mehek's looking up that one, which, Melis, can you tell me what 9 is?
No.
Yashin, can you tell me what 16 is? Elliot, can you tell me what 40 is? Soren, can you tell me what 84 is? Adrian, can you tell me what 96 is? And Luca, can you tell me what 108 is? You will have to look up on a periodic table.
Is it helium?
Helium, well done.
Getting there.
Yeah, 9.
Oxygen. Yeah.
Tommy, which one are you?
I didn't have one.
You didn't have one, so who?
I
Okay.
just said oxygen for 16.
Yashin, how you doing?
Is it oxygen?
Oxygen for 16.
Yeah.
Okay, Melis, have you got 9 yet? Come on.
Yeah,
You should be one of the slowest in the room.
yeah, but it's not. 9 is very. Yeah.
Where's your periodic table? You have a computer in front of you and a planner. There's one up on the wall.
Google it. It's fluorine.
Fluorine.
Beryllium.
Okay.
There you go.
What did you say for oxygen? Yep, sorry, 16. Who was 40? What have you got, Elliot?
Googled it and it said zirconium, but that's not calcium.
No.
Yeah, see, I
it's-
Googled it as
I think
well.
you've looked up the wrong thing. You've not looked up the relative atomic mass.
Yes, I did.
Yes, I did. I googled which element has the relative atomic mass of 9, and it gave me fluorine.
Calcium.
That's not the relative atomic mass. That you've looked up the atomic. Fluorine has atomic number of 9.
It's calcium.
Yeah. Calcium is correct. 84. Who had that? Sorry. Krypton, did you say? 96. Which one? Sorry. The M one. And 108 must be silver. Yeah. Now, classic mistake.
Yep.
2 students made it. Both very brilliant students, is that they get the relative atomic mass mixed up with the atomic number. The atomic number gives you the wrong answer because the relative atomic mass of beryllium is 9, not fluorine. The relative atomic mass of fluorine is 19. Its atomic number of fluorine is 9, okay? Right, moving on. You need to be able to calculate relative formula masses. Relative formula masses are the masses of molecules or compounds. Okay? Basically, I could say to you, how heavy is a water molecule? Now, it's not really made up of sheep, but you know that water's H2O, bonded together. So how heavy is it? Well, what we have to do is we have to find the relative atomic mass of each atom and add them together. Okay? That's why they use RAM for, yeah. So, hydrogen is 1 from the periodic table, oxygen is 16, add them together, and obviously we've got 2 1s, that is going to make 18 overall. So a molecule of water weighs 18 atomic mass units. Remember this?
Yes.
Yes?
Easy.
Right, methane. How heavy is methane? See if you can work it out. First person to tell me, I'll be very impressed with. Come on, methane's an easy one. What'd you say, Baileys? 16, yeah, because it's 12 from the carbon and 4 of those, and the total is going to give you 16, okay?
16.04 grams per mole.
For a mole, that's fine. That's you've got the molar mass by looking it up on Google. That's very good. You're right. But 16 is the relative atomic mass. Let's jump to something a bit more complicated. Sulfuric acid. Who's going to be the first person to do sulfuric acid? H2SO4.
34 plus 48.
How heavy is it? Sorry.
34 plus 38.
That's not an answer. I need an answer.
34.
80.
50.
80. You said 80.
42.
80.
82.
82.
It's 80.
Let's check it. So we've got 2 of those. We've got 1 sulfur, and we got 4 oxygens.
Oh wait, no, I got it wrong. So carbon.
Nobody got it right.
Nice.
Incredible. And I'll let you use a calculator as well.
Look at the carbon because I already
Oh yeah, I did carbon dioxide.
48.
You forgot about that.
You need to get a bit better at those. So, quickly, let's see if we can solve these. We're going to start off, Adrian, you're going to have iodine. Tommy, at the front, you're going to have sodium chloride. Nancy, you're going to have aluminium oxide. Tiff, you're going to have potassium nitrate. And Maylise, you're going to have ammonium carbonate. So, I need you to work out the relative formula mass.
I'm gonna get one.
You're going to need to use your periodic tables.
18 times 2. And up 6. Plus 12.
Right, who did I give iodine to? Adrian, what is it? What have you got for iodine? Come on.
Sure,
It's all you need is your periodic table and a calculator.
ammonium carbonate, 96.
96 for ammonium carbonate. Good man.
I was right.
Hang on. I'm getting there. I'm slow at math. Okay.
This is why you're allowed to use a calculator.
So yeah, 96. I got it eventually.
Very good. Who had sodium chloride? Nancy? Which one did you have? Aluminium oxide. Who had sodium chloride?
Sodium chloride is
58.5, maybe? Are you sure or not? I mean, do you have a periodic table in front of you? Yeah? You're right. It's simple as that. Go on then, aluminium oxide. Nancy, you can do this. Aluminium, how heavy is that aluminium? Let's help her out. I think it's about 27. Oxygen is 16.
Oh, so
24.
24 is not an answer you could choose. Plus, if it's 27, for how many aluminiums are there? 2. 27 add 27 is what? 27 add 27.
54.
54. 16 add 16 add 16.
48. 54 plus 4.
Okay, guys, you need to. These are simple, easy marks. They will give you the formula, and you have to tell them how heavy it is. You need a periodic table, which comes in the exam, or is in your planners. You need a calculator. It's as simple as that. You've got to get these. We teach this to the year 7s. They're getting it right 100% of the time.
Yeah, sir, we got it right in class as well. We just didn't do it
We
in the
got it
test.
right in year 7.
Just didn't do it right in the test, and we've got to get it right in the test. Tommy,
How is sodium chloride 58.5? Because
Right.
are there two chloride?
chlorine.
Are there two chloride?
No, there's only one.
Our chlorine is like
chloride.
35.
Because his thinking told us that chlorine had
You'll get confused with isotopes. There's two different versions of chlorine. The average weight of chlorine is 35.5.
This is the normal.
This is sorry.
So what's the difference between this chlorine and the isotopes?
That's the difference in neutron number.
So okay.
Okay.
Right.
Right, guys, listen up. Shh. No, one of them is 35, one of them is 37.
Yeah, that's what. Yeah.
Right, how many people have come across the term mole before?
I hate moles.
Yeah? A mole, basically, is the mass of 12 grams of carbon. Okay? Now, a mole is a number. Because in 12 grams of carbon, we've got a certain number of atoms. Does anyone know that number?
Avogadro's number.
What is Avogadro's number?
Something to the power of
Isn't
23.
it 6 point something
Six
to the
times
power
10 to the power
times 10 to the power of 23 something?
That's it.
Wait.
6.023 times 10 to the 23. Now, when we're trying to calculate the number of atoms, it would be ridiculous to use numbers when they are as large as times 10 to the 23. That's
Can
23
you just repeat
zeros.
your definition of a mole?
A mole is the number of atoms in 12 grams of carbon 12. Now, if I said to Mehek, go and get me a dozen eggs, how many eggs would I want?
I can't remember.
Well, what can I do this first? Listen first, and then go. If I said to Mehek, I would like a dozen eggs, Mehek, how many eggs is she going to get? 12. If I said to Mehek, go and get me a mole of eggs, how many eggs would she come back with? One? No. No.
No. Less than.
What number have I written up on the board?
1,000.
Yeah, 6.02 times 10 to the 23. Guys, it is just a number. The mole is just a number. Okay, so we have said a dozen is 12, yeah?
Yeah.
A mole is a really big number. But the good thing about that number is it's so big, when we're talking about how many atoms are in 5 grams of this, it comes out to be a nice small number for us to use. I don't go to my technician and go, can I have 5 billion moles of HCl? I go to my technician and go, can I get 1 mole of HCl? I talk about it in terms like that. Does that make sense? Yeah?
No, it doesn't.
Sir.
That makes
Right, okay, I'll try again. I will try again. Alright?
Please.
If I said 2, Maylise this time, Maylise, can I have half a dozen, please?
You get 6.
You go get me half a dozen. I would be,
6.
yeah. If I said to Maylise, go get me half a mole, what would it be half of?
3.0.
It would be half of Avogadro's number. You got it.
3.1.
Okay? That is why we use moles.
0.
We use moles because they're a useful amount. Okay? The mole is just a number. That is all it is. No, it's just that number. It's always that number. And it's, where did they get that number from? Somebody decided they wanted that number because they got 12 grams of carbon 12. Chemists are a little bit obsessed with carbon. Hence we're made out of it, and everything else around us seems to be made out of it, so we may as well use it. And they use that as the standard. The standard meaning we compare everything else against it. So when I get 1 mole of water, okay, how many water particles are in my 1 mole of water?
That many.
That many! If I get a mole of iron, how many iron atoms are in there?
6.023.
You've got it. If I've got half a mole of oxygen, how many atoms are there?
6.023 divided by 2.
Or 3.
It's scary there, but yeah. Yeah, but that is what it means.
3.015.
That is what it means, okay? It's a very powerful thing. Now, here's where chemistry gets really cool. How much
It's not cool.
does... Here's H2O. Let's stick to H2O. It looks like this is oxygen and hydrogen joined up together. How much does one of these molecules, how much does one of these molecules weigh? 18, yeah? Because this is 16 and this is 1 and 1, yeah?
You scared me when you said
Yeah?
the other one.
Now, one of these is 18 molu. So, 1 mole of water, okay, we know is actually 6.023 times 10 to the 23 molecules of water. Does that make sense?
Sway.
But there's a really cool thing. 1 mole of water actually weighs a certain amount. Guess how much it weighs?
That times that.
No.
No.
That would be a massive number.
Yeah, I know, it would be.
Be 18 times.
What?
Yeah, 18 grams.
Yeah.
What the hell? I just said I wouldn't swear. There. A mole, okay, is the same number in grams as the atomic mass units. Okay? So 1 mole of water is 18 grams.
That's so simple.
Hang on a second. What's 1 mole of CH4?
How much does it weigh?
16 grams.
Crikey, how did you get that? You wouldn't have got that at the beginning of this session. Huh?
C is 12.
This is why we do it. It makes life easier. Moles aren't things to be scared of. They're not little furry animals that cause us all sorts of problems in our lawns. They are actually just a big number that make things useful. So we know that this on its own would be 16 AMU, but 1 mole of CH4 is 16 grams. Okay, if I know this, then how much would half a mole of water weigh?
9.
In terms of its mass? 9 grams. And even if you don't really understand that, even if you're sitting here thinking, Christ, I hate chemistry, you are lucky because there is an equation which allows us to work out the moles. And that is the number of moles equals the mass divided by the relative atomic mass. Okay? Or relative molecular mass if it's a molecule. Which is the same as the relative formula mass. Okay? RAM actually has the symbol of AR and relative formula mass actually has the symbol of MR. But what that means is, if I said, actually, Mr. Gould, instead of having 9 grams of water, you've actually got 2 grams of water. Okay? So I've got 2 grams of water. I don't know my moles. What's my moles going to be? Well, don't worry, I divide it by 18, because that's the relative formula mass. 2 divided by 18 is what?
Something.
Sorry?
9.
1 point.
1.111111111.
It would be, what would it be, sorry? 1 point.
1.
Alright, we'll stop there then. But that's how many moles I'd have. I'd have 1 and a bit. Yeah, I don't understand how that's stats.
You said
Can you just put it in your calculator, 2 divided by 18. Ishita, what is it?
1.
0.11. Okay. Does that make sense?
Yeah.
So even if you cannot remember the theory behind what a mole is, which is just a number, like a dozen is 12, a mole is a really big number, Avogadro's constant. Even if you can't remember it, you just use this equation. You learn it because it's useful. It means that if I said to you, weigh out 17 grams of sulfur, you could work out the moles. When you know the moles, you can actually work out the number of particles. Because when you know the moles, what do you do to work out the number of particles? No. If I have got that, how would I work out the number of particles? If 1 mole equals this, I just need to times that by this to work out how many particles are in that. That makes sense? Yeah?
Kind of.
Well, hold on a second. Let's rub out some of this then.
No, don't.
No. If you don't get it, if it's a kind of, we're going to keep going again. So my point is if 1 mole equals 6.023 times 10 to the 23, but I've been told up there that I've got 0.1 moles. How many particles would it be? Yeah, you could do simple maths like that, can't you?
Yeah, no, it's just the way you worded it.
Well, that's the problem, isn't it? And the problem is the way I'm wording it is never going to look as pretty as that. You have to decode it. That's the nature of science. Okay? Moles are not to be afraid of. You need to know your equation and it will be pretty useful to you, okay?
Yes,
So,
sir.
look at this here. Look at the pattern. Iron, relative atomic mass, mass of 1 mole. Same number, isn't it? 18, 18, 24, 24. It's always the same. If you can work out the relative atomic mass from the periodic table or the relative formula mass, you will always know the mass in grams of 1 mole. Right, let's do some true or falses. Okay? True or falses. So, Marvel, the relative atomic mass of carbon is 1. No. Yes, I'm glad. What is the relative atomic mass though?
It's
Nope.
Oh wait, no.
That's oxygen.
Oh yeah.
Please use a periodic table.
Be quiet.
At the beginning of the session, if you are somebody who cannot remember to bring a periodic table with you, will you please grab one of these? Because how many exams have you got? Pass these down. Well, you've got So, all thanks to Marvel, Mr. Gould has walked around the room giving out plastic periodic tables. Hunter, what is it? 12. Relative atomic mass is always a whole number. What do we think? This is actually a tricky question. False, why? We'll see what they say. Chlorine and actually a few others. The relative atomic mass is actually the average. And chlorine has a few different versions. We call those versions isotopes, yeah. Chlorine has chlorine 37, chlorine 35. It's actually got about 75% is chlorine 35, about 25% is chlorine 37. The average, when you work out those, is 35.5. Okay? Adding the relative atomic masses of all the atoms in a molecule gives the relative formula mass. Tiffany, true or false? What do you think? You think true?
Yeah.
Thank you. Thank you. You're right. That's all you have to do. If I say, how much does a molecule of alcohol, ethanol, weigh? You just add up all the atoms from the periodic table, okay? The relative formula mass of water is 18. Tom? Me?
Me?
Tom, at the front. 18. Water. Been talking about it quite a lot today.
It's up there.
It's still on the board. True or false? Is it 18?
No.
It's not 18. Tommy at the back? Is water 18?
No.
Oh, for crying out loud.
Oh, yes.
It's right
no.
there. It's on the board.
Water is made up of H2O.
Sorry.
Oxygen is 16, hydrogen is 1. There's 2 hydrogens to every oxygen, it's 18. Crikey. See what we have to work with. Right, the units of relative atomic mass are grams. Melis.
Wait, hang on.
It is. Yes, because what are the units for relative atomic mass? AMU.
Whoever said it, I heard someone whisper true.
Well, they will say all sorts of weird stuff at points. 1 mole of sodium, 1 mole of sodium has a mass of 23 grams.
Yes.
AM.
Good stuff. Okay. Right, we do not have enough time to do percentage by mass, do we? What time is it? 5 minutes. Should we just plough through it till we go?
Yeah.
I mean, it's only Marvel's parents that are waiting for me.
Yeah.
Wait,
Um,
sir? I didn't.
It's your parents that are waiting for me for parents evening first. Right. If I want to work out the percentage by mass of an element in a compound, I'm basically saying how much of that specific element in that compound is there. Okay? So you know in water it's H2O,
Yeah.
but the oxygen is much, much heavier. I mean, 16 times heavier than the hydrogen. So if I was trying to work out what percent of water was oxygen, it wouldn't be fair to just go, oh, it's a third because it's one of, no. We do it by mass. Okay? Let's look at some examples together, okay? So here's ammonia. Ammonia is a horrible smelling gas. It's NH3. It's made up of nitrogen, which is 14, and hydrogen, which is 1. So if we work out the relative formula mass of ammonia, it comes out as 17. Now if I wanted to work out the percentage of ammonia that was nitrogen, all I need to do is use this equation here. The relative atomic mass times the number of atoms of a particular element divided by the relative formula mass multiplied by 100.
Oh, nitrogen.
So what does that mean? Well, the relative atomic mass of nitrogen is 14. How many nitrogens are in there? 1. Divided by 17 times 100, 82. So what we're saying is, in ammonia, 82% of it by mass is nitrogen. Does that make sense?
Yeah.
Yeah? Let's have a look at some other examples, okay?
Simple.
If we were trying to work out for hydrogen,
This would be 18.
1 times 3 divided by 17, 18%.
Ah.
Okay? Right, have a go at this. Find out the relative formula mass and then try and find out the percentage of oxygen. You're going to have to do some working out.
40. Of oxygen.
Mr. Gould, do you have a marker?
A marker.
Yes.
I mean, that might work.
Yeah.
Now, everyone started off with the first one, magnesium oxide, which is good, but actually, considering we're trying to go through this quickly, we'll let everybody do magnesium oxide, and then Maisie's table, you're going to actually do sulfur dioxide, and Soren's table, you're actually going to do sodium hydroxide, and everyone else do potassium oxide, okay?
What'd you get for the second one, Melis?
You just said not to do the second one. You told me to do this.
That's okay. I mean, if you jump onto the fourth one. What'd you get for the first one, Hunter?
40%.
Yeah.
So, what was this though? Oh, 40? And then you did percentage of oxygen, you got 40%, did you? Brilliant. Has anyone managed to do sulfur dioxide yet?
Yeah.
What did you get? Jordan, what did you get for this? 64? Excellent. What did you get for this? Right, so now you know this is 64, you've got to do the equation, which is,
Over 64 times.
it's actually 16
25%.
times
I was
2,
going to ask what do you mean times 2?
times 2 because there's 2 oxygens.
So that's not
32. 50.
Yashin, what you get?
Potassium oxide.
Yep,
The relative atomic mass is 54.
yep. 54?
94.
Oh.
Sir, it's 50% for the
I
sodium
said
dioxide.
50%?
the percentage is 17 for potassium.
Okay. And this last one, sodium hydroxide. Sorry, your table.
They mixed up the thing, so
40.
yeah, the first one.
40 for this.
Yeah.
And then what's this? I love the way you tell each other.
40% again.
Mr. Gould, they messed up with all their numbers. It's 4, is it? 40%. Now, isn't that interesting? When you look at those molecules, if I said to you, compared to their mass, which one has the most amount of oxygen, you wouldn't have said sulfur dioxide, or probably not, would you? You wouldn't have realised that was 50%, and you wouldn't have thought maybe the oxygen was so little by mass in that one. So that's when we work out percentage by mass. Now the only time, does that make sense to people?
Yes.
The only time this is really useful is if we want to try and make money. And in chemistry, we usually make money by having a product. And one of the products that's really important in industrial chemistry is fertilizers. Because fertilizers are all about getting nitrogen back into the ground so that you can make proteins from your plants and your crops that you'll grow. Hence, if you make proteins, eventually they should end up inside us and make us. Okay? So, we could do an investigation and work out in the different types of ammonium nitrate here, in these different fertilizers, which one has the greatest percentage of nitrogen. And we could use that as a measurement. Now, you might be a farmer one day. Farmers are rolling in it these days. And you'd have to have the chemical understanding to be able to know that you weren't being ripped off by the fertilizer salesman. Does that make sense?
Yes.
So fertilizers come up as a regular question in this sort of situation. Alright? So let me solve these ones for you. Just work out the relative formula mass as before, and then the percentage nitrogen. And as you can see, plant B big is the best if we're thinking about the amount of nitrogen there. Mega pumpkin, yes.
Super gross.
Okay. So we can argue about which one's the best. Remember, we start off today about relative molecular formula. The empirical formula is the simplest ratio. I think we've just about got enough time. If you guys have got a minute, do you remember how we do empirical formulas? How we calculate them?
Oh yeah, you.
Kind of.
What's the first step?
You work out the relative atomic mass, right?
No, well I can find out the relative atomic mass is the periodic table. So what do?
You divide it by.
I divide my mass by the relative atomic masses.
And then you now divide by the smallest number.
Oh, it's like you had an amazing chemistry teacher.
Haha.
Okay?
And
And then you've got a ratio, and then that gives you
CH.
your empirical formula, which remember, doesn't tell you the exact information about that molecule, doesn't tell you exactly how many atoms are there, just tells you the ratio of carbon to hydrogen, the simplest ratio. So, step 1, divide by relative atomic mass. Step 2, divide by the smallest answer. You will then get a ratio. As you can see here, they divided by 1.5. 1.5 divided by 1.5 is 1. 3 divided by 1.5 is 2. We've got it. But you must write down the answer. If you don't write down the answer,
I don't get the mark.
you don't get the mark. So many people leave it as a ratio there.
Okay.
There will be, on the exam, at least one empirical formula question for you to work out. Sometimes it might have more than just 2 elements. Sometimes, though, they might give it to you in a percentage. So say instead of giving us 18 grams, they actually decided to give us, I don't know, I'm making this up on the top of my head, but imagine they said to you, a molecule contains sodium, hydrogen, carbon, and oxygen, okay? And 28% of it is nitrogen, sodium, 3% of it is this. Let's change that to 2 so I can do my adding up. 50% is this. How much would be there as oxygen then?
100 minus all those.
100 minus all of those, what would it be?
20.
20%, yeah? And then guess what? It's really complicated, this step. No, it's not. You just change that into grams.
Oh.
Because what you do is you take a 100-gram sample. And then what's the first step with empirical formulas? Divide by relative atomic mass. Where'd you get those from? Periodic table. Then you divide by the... Then you get a ratio and put it there. What if you got a ratio, though, that was 1 to 1.5?
You times it by 2.
Times them both by 2, that would become 2, and this would become 3. Okay? I'm really sorry we had to rush through that last bit, and I obviously can do this again. If you look, we didn't manage to get onto everything I wanted to do in this session. But it was good that we went through some of this stuff, because some of you were a little like moles. You're like, oh, I hate moles. Actually, why would you be? Who's afraid of a dozen in here?
Yeah.
Yeah, I'm afraid of a dozen out here. You're not really, are you? You know a dozen means 12. Now you know that a mole is just a name for a number. Okay? Next week, next Monday, lunchtime, I'm supposed to be doing exam practice, but I haven't finished everything I wanted to do in this session. So if you want to, come along on next Monday lunchtime and we'll go through some more of this calculation stuff, okay? Monday lunch, during the exam practice. My session next week after school will definitely all finish because it's bonding, it's a lot shorter, so I can cram it all in one session.
Wait,